In section 4.9, we're going to talk about the concept of Newton's method, which is another application of derivatives. To get a sense of what this new application is all about, let's take a look at this opening motivation. Let's suppose that I actually wanted to find a positive root of this function. Notice that would mean where a function like this f of x equals x squared minus 2, where that would cross the x-axis. A positive value of x where it crosses the x-axis. And what if I wanted to find that value to a high level of accuracy? Well, first off, I should note that I can easily come up with a value that can make this function turn into 0. I could easily see here, as I state below, that if I just plug in square root 2 here, square root of 2 squared is a 2, 2 minus a 2 makes a 0. But square root of 2, while I know that that is an exact value that makes this work, I don't know what that exact value actually is, right? Like maybe I want a decimal approximation of that number so I can understand, is this bigger than 1? Is it smaller than 1? Is it smaller than 10? Like how much bigger than 1 maybe is it, right? You know, I might want to ask questions like this. And what if I want to be able to create then a decimal approximation of this value that is very, very accurate? So to do this, we're going to have to go ahead and ultimately start by trying to at least take a guess as to what this value here might actually be. So I'll go ahead and actually write that here. So I'll say we will start by making a guess as to what the value of square root of 2 might be. That's going to kind of be where we're going to start. So we could probably come up with a lot of different possible, first guesses for what this value might be. Now, for the sake of argument right now, I'm going to go ahead and suppose that I'm going to make a guess that, how about the square root of 2 is roughly 2? So I'll say here, let's suppose we start by guessing that square root of 2 is roughly equal to, say, the value of 2. Okay? Now, obviously, we know that the square root of 2 isn't the same thing. I can definitely be aware of that, even if I just think through that, like, the square root of 4 is 2, and this should be less than the square root of 4 because it's only the square root of 2. But again, I need to make a starting guess that's at least kind of in the ballpark. And so I might be able to say, well, maybe the square root of 2 is roughly 2. So here's what I'm going to do. I'm going to take some of our knowledge that we've gathered throughout this chapter and the previous chapters about derivatives, and I'm going to put them to use here. And I'm going to put them to use in the following way. I say that we will try to find a tangent line to the function f of x equals x squared minus 2 at this value of x equals 2. So I'm making this starting guess that the value would be 2, and that's where I'm going to build my tangent line. So if I was to kind of take a quick picture of what's kind of going on here, I could see that, well, the graph of what I'm actually working with is x squared, but it's just bumped down 2 units, and so it's going to look like this, or at least something like that. I can see that what I'm trying to find right here is the square root of 2, and I'm curious what its value is, right? Like what roughly is that? Is that bigger than 2, smaller than 2? Well, if I was to think about this a little bit, I could probably determine that definitely this is going to be smaller than the value of 2, but I'm not sure how much smaller. I know that it's actually bigger than the value of 1, but I'm not sure how much bigger. And so I'm going to go ahead and I'm going to build a tangent line right here on the graph. And if I was to go ahead and sketch out this tangent line, I might be able to see that my tangent line is going to look something maybe like this. And very, very interestingly, once I get the equation of that tangent line, I can think about a way to take my initial guess and improve it. So let's go ahead and first find the equation of this tangent line. Okay, so let's see. First we can note that if we want to create the equation of a line, we need a point. And of course, we also need a slope. The point here isn't hard because I want x to be the value of 2, and I can quickly calculate out that the y value here would also be 2. So this point up here is 2, 2. I then, of course, am going to need the slope of my blue line, but I can get that by just calculating my derivative and plugging in the x value of 2. Notice that my derivative here is going to be 2x, or in this case, 2 times 2, and so I get a value of 4. And so then I can see here that my tangent line is going to have the equation y minus 2 is equal to 4 times the quantity of x minus 2. Or if I simplify this out a little bit, let's see, this would be y is equal to 4x. Let's say I'm going to have minus 8, but then add 2 over, so minus 6. So this here is the equation of my tangent line. Okay, great. So I can see here that my first guess as to what the value of the square root of 2 is, my first initial guess here was going to be at 2. So this is where this green dot is, right? That was my first guess. But now I'm going to take my tangent line. I'm going to find a way to improve my guess. Take a look here at the picture to see how we can make this improvement. What you'll notice is that this tangent line here also crosses the x-axis. But it crosses the x-axis over here at some other value. But what I'll notice is that this value is actually closer to where the square root of 2 is than where we started with originally over here at 2. So I'm going to try to find the coordinates of this x-intercept. But since I'm trying to find this for a line, that's actually going to be really, really easy. So I'm going to go ahead here and say that we will now try to find the x-intercept of our tangent line. This will kind of give us another improved guess of what the value of the square root of 2 might be. So of course, to do this, I would go ahead and say, what value can I plug in for x that would allow me to get an output of the value of 0? Well, again, that's really easy to compute here. I could see that I could crunch this out, add 6 over to the other side, divide both sides by 4, and if I reduce, I'm going to get a value of 3/2. So my next value over here is going to be 3/2. That's where, I've crossed right here 3/2. So now I can go ahead and I can say that this value of 3/2 is my next best guess. So I can see here that we have improved our guess as to what the value of the square root of 2 is. We've inched a little bit closer, and even better, we could repeat this process to improve our guess again and again. That is, I could kind of imagine going here to this picture and saying, okay, so now I'm at 3/2. Why don't I go back up to the curve right above 3/2 and build a tangent line there? Notice that this tangent line is going to look like something like this. Now, this may not cross perfectly over where the square root of 2 is, but it sure as heck is going to be a lot closer. And so if I could find where this new tangent line crosses the x-axis, I could see that I'm going to get a value that's even closer to the correct value. And so this is the general idea of Newton's method, that I can take a tangent line, find where it crosses the x-axis, and slowly keep improving by taking a new tangent line to find where it crosses the x-axis. Then make a new tangent line to find where it crosses the x-axis. And I'll slowly find that all of my x-intercepts will slowly move towards the x-intercept of a given function. Now we can see this actually happening here again in this nice little applet where I'll be able to kind of do a lot of these tangent lines and approximations very quickly. Notice here I have a purple function and it clearly crosses the x-axis at some point. And I don't know what point that is. But maybe I make an initial guess. Maybe I say something like, I think it crosses at I don't know, let's see, maybe like 2.30715, right? Maybe that's like my first guess. So I go there and I say, well, that's obviously not where it crosses, but it's kind of close. So I go up and I build a tangent line that you can see here in green. And down here at B is where I end up getting a new x-intercept. But notice that if I went from B and I went up to the function and drew a new blue tangent line, I would get another point here that crosses. And the x-intercept here is going to be slightly improved now. Notice that I started with a guess of 2.307. I've improved my guess to 1.60 and change, and I could kind of keep going. Every time going up to the function, drawing a new tangent line, and you can see that eventually all of my tangent lines begin to start crossing the x-axis around a very, very, very similar or common point. Notice here as I start to draw tons of different tangent lines, their x-intercepts are all narrowing in on exactly where I cross here. And so this is the idea of Newton's method, to use tangent lines to help us find roots of functions.